Welcome back to another video. Here, we will talk about Central Limit Theorem. The normal distribution is defined by two key parameters. Mean. The mean represents the average or central location of the distribution. It is the point where the peak of the bell curve occurs. In other words, it shows the typical or expected value of the random variable. Variance. Sigma square. The variance measures the spread or variability of the distribution. It tells us how far the data points typically are from the mean. A larger variance means the data is more spread out, while a smaller variance means the data is more concentrated around the mean. Together, the mean and variance fully describe the shape and spread of a normal distribution. The normal distribution is symmetric around the mean, and the shape of the curve depends on both the mean and the variance. While the mean dictates where the distribution is centered, the flattening or thinning of the curve in a normal distribution occurs due to variance. This happens because the total area under the curve must always equal 1. The area under the curve represents the total probability of all possible outcomes, and since probabilities must sum to 1, any change in the width, due to variance, of the curve must be compensated by a change in height. When the variance increases, the curve becomes wider and flatter. This means that while the distribution becomes more spread out, the total probability must still be 1, so the peak of the curve becomes lower to maintain this total area. Conversely, when the variance decreases, i.e., when the standard deviation is smaller, the curve becomes narrower and taller, concentrating more of the probability around the mean. In both cases, the overall area under the curve remains 1, which is a fundamental property of any probability density function. The standard normal distribution has a mean of 0 and a standard deviation of 1, making it a special version of the general normal distribution, which can have any mean and any standard deviation. As you may have noticed, unlike the other continuous distributions, we have not yet introduced the CDF of normal distributions. That is because normal distributions don't have closed-form CDF functions where we can get the probability just by simply plugging in the value of x. To standardize a normal random variable, you convert it into a z-score by subtracting the mean and dividing it by the standard deviation. This process transforms any normal random variable into a z-score, which represents how many standard deviations the value is away from the mean. The resulting z-score follows a standard normal distribution, with mean 0 and standard deviation 1. The central limit theorem is a fundamental concept in statistics that states that, regardless of the population's original distribution, the distribution of the sample mean, sometimes even other sample statistics, will tend to be approximately normal as the sample size increases, provided the samples are random and independent. This holds true even if the population itself is not normally distributed. The central limit theorem becomes more accurate as the sample size grows, typically when the sample size is greater than 30. The theorem also tells us that the mean of the sampling distribution will be equal to the population mean, and the standard deviation of the sampling distribution will be the population standard deviation divided by the square root of the sample size. The central limit theorem is crucial because it allows for the use of normal probability methods in inferential statistics, even when the underlying population distribution is unknown or skewed. The rule of thumb for many practical applications is to use a sample size of at least 30, as this ensures that the sampling distribution of the mean is approximately normal for most population distributions, even if the population itself is skewed or non-normal. But there are cases that even smaller sample sizes might work. If the population is normally distributed, any sample size will work well because the sampling distribution of the sample mean will already be approximately normal, even for small sample sizes. If the population distribution is symmetric and unimodal, has a single peak and is not too skewed, a sample size of around 4 or 5 is often sufficient to approximate a normal distribution for the sample mean. Let's go over an example together. We roll a die for 10 times and find a mean. Then, we will repeat this process for 10,000 times. Let's find the histograms of the die outcomes and the means. When we roll a die 10 times and calculate the mean of those 10 rolls, we're getting one sample statistic, the sample mean. Each time you repeat the process of rolling the die 10 times, the outcome will differ due to the randomness of the rolls. Over the course of 10,000 repetitions, you will generate 10,000 sample means. When we roll a single die, The possible outcomes for each roll are 1, 2, 3, 4, 5, or 6, all with equal probability. Looking at the histogram of the individual die rolls, it is roughly flat, with each outcome appearing approximately 1/6 of the time. According to the Central Limit Theorem, as you repeat the process of rolling the die 10 times and calculating the sample mean, the distribution of the sample means, after 10,000 repetitions, will tend to follow a normal distribution, regardless of the original distribution of the die rolls. The mean of the sample means will approach the true population mean, which is the expected value of a die roll, 3.5. The spread of the sample means will be smaller than the spread of the individual rolls because you're averaging over multiple rolls each time. The standard deviation of the sample means will be smaller than the standard deviation of individual die rolls. In the United States, the heights of adult men have a mean of 69.1 inches and standard deviation 2.9 inches. If we take a random sample of 30 adult men, what is the probability that their average height is less than 68 inches? What is the probability that their average height is between 68 and 70 inches? Please pause the video here and take a moment to answer these questions. The sample size is large enough to safely assume X bar is normally distributed. The mean of this distribution with the same mean of the original population, which is 69.1, while the distribution should be reduced to 2.9 divided by square root of 30, which is 0.53. To find the probability that their average height is between 68 and 70 inches, we need to subtract the cumulative probabilities of 68 and 70, which is about 0.94. Thank you for listening to this short lecture on Central Limit Theorem.